Yeah, so maths for the HSC. Yeah, if you want the recording, I can send it to you. Okay. So like, so maths in the HSC is like the big idea is calculus. Okay. Do you guys know what calculus is? Nothing. Yes.
I know like not much, not at all actually.
All right. Maybe you heard of it. I guess. Okay. So I'll give you a big idea later. But so there's one thing to have the big idea, and there's other things, the details, right? So it's kind of like the difference between like having the battle plans for the war and actually like fighting on the beach. It's like a different thing. So these are like the algebra. So school math is mainly just algebra. Okay. There's other things too, but they've kind of. I mean, algebra is a pretty key thing. Um, so we might need to know how good you are at algebra. Do these questions look easy?
Yeah, there are.
Look easy, yeah. All right. So then let's just do one to kind of. How about one each? Yeah.
Uh,
All right. Someone give me this one, and someone give me this one. Maybe Slava can give me this one.
Okay.
Yeah, and try to interact as much as possible. Then I get as much information, and I can work with that as much as possible.
Do we write the answer down?
Oh yeah, just right. That's your paper. Yeah. If you want more paper, just let me know.
but which one are you doing?
I'll do X.
I need to.
Okay, that leaves you with V, Slava. Okay. Huh. Do we get these things?
Yeah.
All right. So Slava told me that this was 4 outside of 2x squared plus 5. Yeah. And then Aiden, what's this one?
15 bracket 2y cubed minus 1.
Keep minus 1. Yeah. Okay. And Kate?
14 bracket 3y plus 2x minus 4c.
Oh, good. Okay, so I guess naturally you viewed the question as trying to keep them as whole numbers, you know? There's a little bit of a weird thing with this question, like what if you had like 8 outside of x squared plus like 20 on 8, you know? Okay, that's kind of possible too. I guess it's I think this is probably preferred, you know? But you should be able to see this stuff like is possible too. Okay. So the funny thing with these kind of exercises is the exercise is always of this form like factorize, right? Whereas the actual real life examples of the questions is like it just comes up like that and you're expected to be able to factorize. Does that make sense? It doesn't tell you to factorize. And so but you see a factorization and it helps you continue. You know? Okay, so this is good. What if it was 15y cubed minus 1? 15. Would that make a difference? And what would happen?
Oh, it would be 15 bracket y cubed minus 1.
Okay, and then what would be the difference from here? What's the difference?
The other question is 2y.
Yeah. Okay, and then what are the implications of that difference? Slava, you can answer it too, you know. So if it was this, or if it was this, so there's a 2 there and there's no 2 there, yeah? What difference does it make? Hmm. Twice as many y in the first. Okay, no. So yeah, I was just, there's twice as many, but what does that mean? What is the
Like when you expand, it's different.
expand? So when you do something, so I guess, okay, I can phrase it in a little bit more mysterious way. How about this?
Okay.
So if the question was this and you wrote this as the answer, you get full marks. Okay? If the question was this and you wrote this as the answer, you get 1 mark of the like 2 marks. That's already enough of a difference, right? So doesn't that sound very weird? It's like there's a 2 there, you don't have to, you get one out of 1 mark. If there's no 2 there, you get 1 out of 2 marks. Why is that? I'll give you a few minutes to think about it. I'll be right back. Figure it out.
Is it because you can like factorize it differently?
Sort of. Wait, what is Slava saying? Yeah, have you heard of difference of cubes?
Oh yeah.
So if you have y cubed minus 1 cubed, you can actually keep factorizing. So if the question was factorized fully, you would not have factorized it fully. You know? That makes sense? No. Yeah, so factorizing, so we call it factorizing when we write something like that with more brackets timesing each other. Yeah? And we call it expanding if we go that way. Yeah? So it's always easier to expand. So that's why factorizing is something that's more, it's what you use. Expand is what you use to prove the factorization. Okay. Okay. So Yeah, even at the very basic level, I think, because you're never told to factorize. Okay, that's the key. So you have to have a sense for when you want to factorize. I mean, I think in general, like if you can factorize, you probably would. Yeah. But so like if you see a factorization, you probably do it and hope for the best anyway. But there's some situations where factorizations are going to be good no matter what. Okay, do you know what situation is going to be really good for factorize?
Maybe a question.
So in equations, but what kind of things in the equations?
Like if both the sides have a common multiple factor.
Yeah, like if like you can set the equation to equal 0, right? Yeah, because if you can factorize the equation is equal to 0, then you reduce the equation into the equations with the factors are equal to 0. You make it a simpler equation, right? Okay, that's very good. And then there's another one that's kind of I think that's missed a lot. It's when you have fractions. Okay, when you have fractions, because when you factorize stuff, and there's the same, it's the same with the equations. You said there's factors on both sides. You can cancel the factors. Yeah, that allows you to make it simpler instead of getting bigger. Okay, so there are lots of things like even in calculus where it's like you have to do some procedure with some expression, right? And instead of um, and in school maths is always like that. You always have a procedure, and the procedure works for everything. So you have like quadratic formula, solve all the quadratics. Yeah, you have all these procedures. Okay, but following the procedures is usually never the right way to go. Okay, even though that's how they tell you to do it, and that's what the answer says it is, and that's what the sample answer says it is. Following the procedure is usually always the wrong way to go. Okay, and the fundamental issue is okay. The procedure works for everything. Okay, so the good thing about the procedure is it'll work, okay? But it doesn't necessarily work the best for any one thing. Does that make sense? Like you don't need a quadratic formula to solve x squared equals 1. You know what I mean? And that's kind of what I guess maybe highlights the difference between Olympiad maths and school maths. But it should give you an idea of like how to really do maths. Because if you're alert to the specifics of the problem, you'll be able to do it much more efficiently than if you just apply a procedure mindlessly. Okay. But at the same time, if you know the procedure, it's a backup for when you can't find that really quick solution. You know what I mean? Okay. So factoring is going to be really helpful um, because it keeps things simple. Okay. So even when you do calculus, it could be some complicated procedure like differentiating this fraction, but it looks really easy because it actually just cancels out. Okay. We'll get to that in time. All right, let's have a look at more examples. Um, all right, maybe we'll do. Let's do yeah, if you've kind of done your one, you can move on to we'll do the bottom three of every like yeah. You can stake the one that you want to do.
At the end.
And okay, so Aiden does N.
I'll do O.
Uh, oh, there's another N here. Okay. So Sava's doing P. Alan P. Okay. Yeah. So would you say you would do extension 2 maths if you could?
Yep.
Okay. No. It's a shame the schools don't let everyone who wants to do it do it.
Yeah.
No. But I think there's also some people who want to do it sort of, they're not very well informed. They just want to do it just to get the marks. Aiden? Okay.
6x bracket 4x minus 3.
6 brackets 4x minus 3. Okay, that looks good.
And then 11h bracket 6 g squared plus 2h.
G squared plus 2h. Yeah.
15y bracket 3y plus
15y bracket 3y plus 4. Okay, good. Now it's got w, 7w plus 2. Oh, you kind of wrote it backwards. Oh no, wait, that's not backwards. 2xy 2y plus 3 plus x. Right, did you mean x? Typo, okay. Then, oh, K for m.
Oh, sorry. N bracket 6 minus 7.
M and 6 minus 7m. No? Yeah, so usually, yeah. It's one of those things like when you're able to just manipulate algebraic expressions, like when you're doing even like extension 2, the problems are like, you're like, oh, this problem is so easy, you just have to manipulate the expressions. But then but the problem is when you don't know how to manipulate expressions, it becomes very difficult. So this is what one might call a necessity. Okay, so necessary stuff, they're not very important until they're missing. So classic necessities are like air, food, shelter, water, money. They're not important on their own, but when you don't have it, it's actually devastating. Okay. All right, that's very good. Yes, I haven't watched any of their videos and stuff, so I don't know if they're gonna do the right stuff or not. But we can definitely do our own thing. Okay, so let's go Aiden, Slava, Kate. Okay. Have you heard of the word polynomial?
I've heard about it.
So these things are all polynomials. Okay, so they got the polynomials in one variable, so they got like an x, an a, or a w. Okay, and they have like no fractions, and it's always like whole number powers. So these things are examples of polynomials. Okay. Okay, 4a squared a cubed minus 3. Okay, so here's 4a squared a cubed minus 3, yeah? Yes? Okay, then let me ask you another question. If this number happens to be 4a to the 5 minus 32. No. If that was the question, would the answer be different? But a squared. So what would the answer be?
4a squared bracket a cubed minus 8 is no 8.
Mm-hmm. And then what's the difference between this and this? Okay, so Slava said then factor difference of cubes. So see 8 is 2 cubed. Yeah. So kind of in that same situation we were in before, right? It's kind of like things which can be factorized further. Yeah. So it's good to get the first factorization, but what if you can keep going? Yeah. That makes sense. So that's the kind of thing I think like you see a lot more in an extension, like just having an extra factorization. Um, yeah, but never do they. Well, actually, I think in some of the earlier questions in like the test, they actually tell you to factorize. Yeah, but if they tell you to factorize, then it's probably more likely to have an extra factorization because if they already told you to factorize, then there's got to be something more to it. Yeah, so the harder questions might have like an extra factorization. Okay. Um, actually, if you're working in like sort of, so we're kind of working in the integers. Does that make sense? So we all got whole numbers. But if you're working in the real numbers, then that's when you might get like fractions or square roots and stuff. When you get working in the real numbers, you can actually always factor it to like quadratics and linears. And if you're working in the complex numbers, you can actually get everything down to linears. You know what I mean by linear? So linear is like when the power is just one. So here's a cubic. Here's like a quadratic, the power is two. You know, linear is like if it's just um power is like one. So like here it'd be like x times x. If y was like two, it'd be like x times x plus two. X plus two would be linear and x is linear. You know? Um yeah. Yeah. I think a lot of the things you don't really need to name them. Because a lot of the time you can just go with your instincts. Okay. But to name something is kind of recognizing you've seen it before. So then you don't have to work it out again if you can remember exactly what you did last time. Okay. Oh, so Aiden, what's this one?
3x bracket 4x cubed plus 5.
4x cubed plus 5. Okay, very good. Yeah, so if you're working in the real numbers, you can even think of that as a sum of two cubes, right? But it's just not very nice. It's like the cube root of 5 cubed, the cube root of 4 cubed. It's not necessarily very nice. So then we just say that's finished over the integers. Okay. Um, yeah. Kate.
W to the power 7 bracket 8w squared plus 1.
Yeah. Yeah, that's very good. Yeah, so you were saying like if you had an equation that would be helpful, right? So if you were solving this equation equals to 0, yeah. you'd get this equation equals to 0. You know? And how would you solve an equation like this?
You divide the w to the power 7 by 0.
Divide it. Okay, so then we get this lesson early. So divide. So divide.
Wait, can't you like not divide because then you're assuming w does not equal 0?
Yeah, so the divide thing is like, so you can divide, but you have to assume it's not 0. Okay? So this is literally like 12% of marks in every exam. Okay? So it's like the idea of solving an equation. So what happens is, so division, okay, like, so that's why polynomials are nice, okay? Because polynomials is exactly what you get by addition, multiplication, subtraction, yeah? And what's nice about those things, they work for every single number, okay? That's kind of what algebra really is, okay? Because you don't know what the number is, you gotta only do things that work for every single number, yeah? Okay, but then you get stuff to like division, okay? So division, does it work for every single number? It doesn't, okay? So when it doesn't work for every single number, you have to think every time you do it. So you're kind of forced to think. Because you have to, if it doesn't work for every single number, when you do it, you're forced to think if it's a number that it works for or if it's not. Okay? And what numbers does division work for and which numbers don't? So you can't divide by 0, yeah? Okay. So yeah, so the thing about division, it works for every single number except for 0. So literally to divide, you just need to check the number 0. Okay. So you can divide by w to the 7, but then you have to make sure it's not 0. Okay. So so every time you do something like that, there's two cases. So either w to the w7 is equal to 0, or it's not equal to 0 and you divide by it and you get 8w squared plus 1 equals 0. Yeah? Okay, and then what happens? So you have two equations to solve basically, right? This one and this one. Okay, I mean, okay, so you can see this one, right? W to 7 equals 0. It's maybe not as obvious as it looks, but so that's if w to the 7 equals 0, that means w has to be 0. Does that make sense? You know, because if you're taking a 7th power, you can always do the 7th root. You know, so in this particular case, because it's odd, you get w equals the 7th root of 0. You know, which is 0. Okay. But you can also think of it like this. It's also w times w to the 6. You know, equals 0. Or if you want to do like w cubed times w cubed equals 0. Yeah. And the point is, if two things times together get 0, one of them has to be 0. So in this case, I guess it's easier to conclude w cubed equals 0. Yeah. If w cubed equals 0, then it's w times w squared, right? And one of them equals 0. But if w equals 0, then w squared also equals 0. So either case, w squared equals 0, right? And if w squared equals 0, because w times w, then w has to equal 0. Yeah? So, I mean, yeah. It's really about being sure of something. Do you understand? That's the quality of the mathematics. That's why it's impossible to have quality mathematics when you're in primary school. Okay? It's just all a bunch of kids just doing it as fast as they can, and they're all wrong. Okay? There's no quality about that. Like, so I mean, like a really good quality, like it's like if you like really trust some calculation, you know what I mean? It's like what if your entire like finances depended on it, right? It's like, would you trust it or would you get someone else to do it? Okay, and then if they get someone else to do it, would you trust them? Okay, how do you know you're right? That's the fundamental quality of mathematics. Okay, so maybe I had a quick way to get that it was 0, but I wasn't really sure it was right. But I have a long way, but I'm really sure I'm right this way. Okay. And then people are like, well, you don't have time to do that in the exam. And I was like, well, you probably don't have time to do that in the exam, right? But you have like 4,000 hours before you get into the exam. Okay. So um okay. Okay, and then we have a controversial answer from Slava here. Okay. So here we have Slava said that W equals, so I guess what you did was you put it on the other side. So 8W squared equals -1. Yeah. W squared equals -1 on 8. Yeah. And then W equals the square root of -1 on 8. Yeah. Is that what you said? Okay. What's the controversial answer? Why is this answer controversial? Do you agree with the answer? Disagree? Agree?
Yeah.
Okay. Hayden?
Um.
Agree, disagree, or don't know, or controversial?
Uh.
Now that I've said it's controversial, Slava also can contribute his agreement.
I don't know.
Okay. Okay, so Slava has resolved half of the controversy. I'll give you some time to resolve the other half while I explain the first half. So the most obvious, I don't know if it's the most obvious, the most glaring controversy here is you're square rooting a negative number. Yeah. Okay, so out of like the marks that, like, there's another 3% of marks lost in all exams from um actually there's some other thing about this that's not square rooting a negative number. Square rooting a negative number is actually pretty advanced. Okay, so why can you not square root a negative number?
Because the product of a negative number has to be positive and negative. So if you square root, then like value has to be the same. So
Yeah, so something times itself. The signs have to always end like the same sign always ends up as positive, right? So if it's a real number, then anything squared is positive, right? So you can't something squared can't be -8th. Okay, all right. But when you get into extension 2 maths, okay, you actually expand the numbers you have. You have more numbers, okay? So you don't just have real numbers, you have what's called complex numbers, which covers the real numbers, okay? And when you have complex numbers, you can actually get the square roots of -1/8, yeah? It's just that they're not real numbers, yeah? You created the numbers to satisfy this condition, okay? Because there's no numbers currently that do that, all right? Slava, did you find the other thing that was wrong? No. Okay, so this one actually is along the lines of the divide by zero. Okay, so divide by zero. See, if you didn't account for divide by zero, you'd lose this solution here, right? W equals zero. You just get this. Okay. The thing that happens here. Okay, so what does this symbol mean? Do you know what this symbol means?
Square root.
Square root, yeah? Okay. But there's a longer name for this symbol which actually emphasizes the issue here. It's actually also known as the positive square root. Okay? So why might you emphasize positive square root? You know what I mean by positive square root? Have you guys done quadratic formula?
So
Uh-huh. Do you remember what the quadratic formula says?
no.
Alright. There's like something something plus or minus root something over.
Oh,
Yeah?
Mhm.
No?
it's like I forgot but I know generally it's like plus or minus
Yeah.
square root.
Yeah, so I guess the thing I'm after is the plus or minus, okay? See, this is the positive square root. The reason why a positive square root is emphasized because every number has two square roots. Yeah? It could be negative or positive. Because 1 squares to 1, but negative 1 also squares to 1, right? And so forgetting about the 0 is very similar to forgetting about the negative square root, okay? So this is why like the people come to me, the exam was easy, I got everything, and then they only got 80%. But everything means 100%, right? So where did the 20% go? It's like dividing by 0, negative square roots. There's this kind of stuff, yeah? So, I mean, like, if you're kind of, if you're kind of like, if your brain's developed enough mathematically, you'll kind of feel something's wrong sometimes when this happens, yeah? Okay, and then you might catch yourself. But at the same time, it's really the same issue every time as well. So if you just kind of think about it that way, then you'll kind of quickly know you forgot the minus sign. Okay. So it could actually be if this is allowed, then it has to be plus, and it could also be minus. That makes sense. And in general, when you have a polynomial equation, if the highest power, so the power here is 9, right? There should be 9 solutions. Okay. It's just in this case, 9 solutions if you're allowed to do this kind of stuff. Okay. But see, sometimes the solutions repeat. So you got 7 of the solutions are just 0. Okay. And then here what we say is there's no real solutions. That makes sense? Yeah, so quadratics are kind of funny, right? That's the first time you have a possibility of having more than one solution. Okay. But you can also have like both solutions being the same, so it's kind of like one solution. Or you could have like this situation here, there's no solutions. Yeah? Okay. Yeah, so I'm glad you mentioned equations and stuff. Um, yeah, I guess I could have asked this at the start, but I was like, do you guys have anything? I'm gonna go to the theory next. Um, I feel like we need a little bit of theory, a little bit of problem solving to make it kind of a good balance. But do you guys have anything you want to ask? Like any questions from school
I don't think so, no.
Okay. I mean, in general, you can just like we have 2 hours every week we meet. You can bring stuff to discuss if you want. You know, or if you put it on the Discord and I find it interesting, we can bring it up. But yeah, so also like yeah, it's a two-way process. I can get information about you. You can get information about maths. You know, so even just this like 4 questions, it's giving me a very clear idea of your abilities in these topics, you know. Yeah, I think the problem is a lot of it comes from the way you're used to doing things, yeah. Because I doubt that people really check your homework, right? And if they check, they might check the answer or something. Every 5 questions. I don't know. But sometimes the premise of the questions are very dubious as well, right? Because yeah, like it's a factorize this, but you'll never be told to factorize. Okay. Okay, let's take a little bit of an interlude before. There's only so much algebraic manipulation one can take in one go. But it's one of those things, it's like once you get to do it properly, you'll find that kind of thing relaxing. Like I don't know. It was kind of just kind of like easy to do. But at the start, you need it to be a little bit stressful so you don't make the mistakes. You know? But once you got it, you don't have to think about it too much because you've already understood the whole thing. All right, calculus. You guys know what a limit is? No? Okay, that's good. So, limit. So this kind of thing is actually very funny. It used to be in the 2-unit course, okay, advanced course. And so it used to have a definition, okay? And then the definition is it's very kind of what's called, it demands a high level of rigor, okay? And then you have these limit laws, which is kind of like how to use them quite quickly, right? And then you do calculus, okay? And now you still have the limit laws, okay? But they deleted the definitions. So then in some sense you can't be wrong anymore because it's not defined. Okay, but I guess the good thing about a limit, okay, is you've actually seen them before. Okay. So the earliest time you've seen a limit, I think if it's the same with my schooling, it would have been in year 3. Okay. So in year 3, they were like, okay, so if you write a quarter as a decimal, right? It's 0.25. And then they're like, okay, you write a fifth as a decimal, it's 0.2. Yeah. Okay. But then what if you write a third as a decimal? Or how do you write a third as a decimal?
0.3.
It's like you can't finish writing it, right? It just keeps going forever.
Yeah.
Okay. So, or like you're told to write like with a repeat at the top. Yeah. So, yeah. So this is, I guess, what like a limit is, because what you have is you have a sequence. Okay. You have a 0.3, 0.33, 0.333. Yeah. And it keeps going. Okay. And then we're kind of saying the limit of this sequence. So maybe there's n threes, yeah. So maybe this is like the first term is n equals 1. This is n equals 2, yeah. This is n equals 3. And if we're saying n goes to infinity, it goes really big, okay. And we say the limit is a third. Does that make sense? So we already have some notion of a limit. Yeah. So it's kind of like this kind of decimal expansion is not really the same kind of decimal expansion as the other one. Yeah, there's something different about it. So we got some convention going on, okay? And then we're saying it's actually equal to the number. You know? So the actually equals is this limiting idea. Okay. Just to get you used to some ideas. You know how to round numbers? So if I ask you to round 0.6 to the nearest whole number, you round that to 1, right? If I round 0.4 to the nearest whole number, go to 0, yeah? You round 0.5 to the nearest whole number, what do you get?
1.
1, right? If you round 0.49,
0.
0. Okay, and then here's the one that kind of, but if I put the 9 repeater, what does that get rounded to?
I would say 0.
Okay, so 0 with a question mark. Anyone say 1? Kate, Slava?
Oh, 0?
0, okay. Slava?
Yeah, I'll say 0.
Oh, you all say 0. Well, that means I made a good question. Okay, so this actually rounds to 1, okay? That's crazy, right? You wanna know why it rounds to 1?
Yeah.
Okay, so this is actually equal to 0.4. Does that make sense? So this thing here is actually like, it's not really saying what the number is. Yeah? That's kind of what I meant by like the limit. This is actually giving you sort of like uh, almost like false information. So, okay, maybe something that's more obvious is, can I convince you that 0.9 is actually equal to 1? Oh, connection lost.
Oh yeah, I remember that. Because it's like
Slava's
1/3 plus 1/3 plus 1/3.
okay, so you hear what you get what he's saying? Because if a third is 0.3 repeater, right? Then 3 times that is 1, right? But 3 times 0.3 repeater is 0.9 repeater. So 0.3 repeater is equal to a third, right? So 3 times 0.3 repeater is equal to 1, yeah? And 3 times 0.3 repeater is 0.9 repeater, yeah? So 0.9 repeater equals 1, yeah? I mean, it's very similar. I mean, if 0.9 repeater equals 1, right? Then what does 0.09 repeater equal? Zero point, right? And then what's 0.4 plus 0.9 repeater? So 0.1 plus 0.4. No? Oh, sorry, 0.09. Yeah.
Oh. 0.5.
Yeah. But it's also 0.49 repeater, right? See? Yeah, so that's why we're gonna be careful. Like when we have the decimal with a repeater, it's actually kind of it's actually it's not immediately telling you the number, it's telling you like a limit. And then you realize the limit's actually equal to 0.5. Okay. Okay, so I've been kind of mysterious about what a limit is, but so here's like a definition. Okay. So if I say limit as an, if I say this sentence equals 5, okay. So this is where you have to like switch your brains, really like precise listening for the next minute. Okay. Okay. I can get as close as I want to 5, right? Using the ANs, provided the n's are large enough. Does that make sense? So so the an in our case, right? So maybe in our example, it's like limit n goes to infinity, okay, and it's like 0.3, and there's n threes, right? And we're saying that's equal to a third, you know? So I can get as close to a third as I want, yeah, if I take enough threes. That's what the definition of a limit says. Okay. So sometimes the limit doesn't even exist. Okay. Because there's some things that don't get close to something. There's some things like if it gets a 1 or -1, it's not getting close to anything. Okay. But you can see here, the more and more threes you take, the more it's going to be looking like a third, right? So you can agree, like for example, you can get within 1 billionth of a third by just taking n to be more than 9, yeah? Like in 9 decimal places. Yeah. That's the good thing about limits. It's kind of like there's some sort of error, but you can control the error. You understand? And that's what makes it really like practical to work with limits, because a lot of the time in real life, like you don't really care about the error so much as you can control the error. That makes sense? Like if you just care about the measurement, right? Like your ruler is only accurate to like whatever the lines go to. Yeah. So there's no point having the ruler be accurate to only the lines and demanding the other things be like infinitely accurate. You know what I mean? So you only need other things to be accurate enough that the ruler can't tell the difference. And then it may as well be infinitely accurate. Okay. Yeah. So that kind of so now you don't have to do these manipulations. You can kind of directly know why 0.9 repeater is equal to 1, right? Because 0.9 repeater is really just this limit. That's what that's saying, okay? And saying it's 1, well, 1 is something that you can get as close to 1 as you want by just taking more 9s. That makes sense? Okay. So if you wanted to say that formally, it's like, it actually looks pretty alien if you want to say it formally. Maybe this is why they removed, well, they never actually put it in the syllabus, I don't think. They just pretended to define it. Like they removed something they never even executed on. But okay, so if you look at this actual definition, it's pretty insane. So for all epsilon greater than 0, there exists n natural number, yeah, such that for all for all n greater than n, yeah, an minus 5 is less than epsilon. So it's meant to be the same as what I just said, but it looks so alien, right? So how does this correspond to what I said? Well, I said you can get as close as you want to a third, okay? So this epsilon is what represents that level of closeness. So I want it to be within epsilon of this. That's what. So for any epsilon, I can get it within epsilon of 5. Yeah, so that's what I mean by as close as I want. So like a translation between maths and English. Okay. Okay, and there exists a number such that for all the terms that are beyond that number, the difference is within what I want. Yeah. So what does this exists a number mean? So I was saying as long as n is big enough. Yeah. So what does n being big enough mean? Means it's bigger than this number here. So that's the enough. Okay. So what's enough? Well, that thing. Okay. So there's some point for which when I get bigger than that point, it's enough. Yeah. So for example, if I wanted to get within a billionth of a third, I would need to take at least eight n's. But once I take eight n's, any number more than eight is enough. Yeah. Okay. Yeah. So you can kind of see why they don't really do definitions because it'd be impossible for them to execute in school. Um, but also don't think you can just subvert the definition because a lot of the time you can do the problems without really understanding it. But the problem is like when you get the harder problems, you're back to square one. Okay. So if you do maths in uni, you're going to be learning this again, but with the definitions. Okay. Um, but this is something that everyone finds really difficult. So even the people like that end up, doing well in high school maths and do maths degrees, like they fail when this stuff comes out. Okay. Um, yeah. But the thing is, like, I didn't really have my chance to fail because I kind of saw the other people were failing ahead of me, so I kind of anticipated it and kind of got ahead of it. But this kind of stuff, yeah, so it's beyond expectations for you to understand this, but I think just trying to understand it will make you better at the other stuff, which you do need to know. Okay. All right. Any questions about that? Okay. So these are limits of sequences, okay, which may or may not exist. You could also have limits of like functions. You guys know what functions are? Functions. So functions are like, yeah, Slava knows what functions are. So so I guess the easiest functions are like the polynomial functions. Okay. So if you have like a polynomial like x squared plus x, okay, like what are you most tempted to do when you see something like this? Well, you're tempted to sub in values for x, okay? And the act of subbing in values for x makes this what's called a function, okay? So a function is something like abstractly, a function is something that just takes inputs and gives you outputs. Yeah. Um, More formally, you need to define the set that it takes inputs from very precisely. It's called the domain. Okay, so usually we take like the set of real numbers. Have you seen this symbol before? This is the set of real numbers. Okay, we usually take that as the domain. Okay, so that means, um, so if I sub a real number in, I square it and then add itself, I get some number, right? So that's how this defines a function. So the input is my real number, so I could input like 2, right? And the output is 2 squared plus 2, which is like 6 or something, yeah? Okay, so that's like a function. Okay, but it's a particularly nice function. Okay. Um, so when you have a function, you can call it something like f(x) equals that. Okay. So the x represents the input, and the f of x represents the output. Yeah. In school, it's kind of abused because you don't really distinguish the difference between the function and one of the outputs. Because the functions that you in school are usually always given by a formula. Okay. So it's always very nice. So in this case, the function is whatever number you put into it. So can some guy tell me what What's f of 5? So f of 5 is by definition the output when you input 5. Right? Okay, and in this case, it's given, the function is given to you by this formula. So you literally just replace the letter x by 5. Okay, so you get 5 squared plus 5. And so that's like 30. Yeah? Okay. So that's the gist of what a function is. Okay, and you've probably learned how to graph stuff, sketch graphs. Yes? So if you were to graph this function, or it look, what would that look like? How would you know what that looks like? X squared plus x. So put y and x. Y equals x squared plus x. You guys know how to sketch this graph? Alright, so one thing is, do you guys know what a parabola is? You know, like it looks like that, right? So one way to sketch this graph really easily is to find out where it hits the x-axis. Yeah. And then you know it kind of has to look like that. Yeah. Where does it hit the x-axis? So the x-axis is where y equals 0, right? Okay. Yeah, so then we set this to 0, so x squared plus x equals 0. Yeah. So this is a situation where naturally the equation comes up, right? You kind of never really asked to find an equation, never asked this whole equation, but you can, right? So that's what, it's the same in like sport, right? Like, it's like, you're never really told what to do. You're just told how to win. Like there's the rules, right? You score more points, you win, right? But you can do it however you want, right? So a competitor who wants to win would probably want to do the things they're good at and avoid the things they're bad at, right? So I guess we take this route because we just got good at this, but we don't have to take this route, you know? It's the same for you. Like when you have options, you do what you're good at, right? It's just if you're good at everything, then it doesn't really matter. Or if you're bad at everything, it doesn't really matter either, right? Okay, so how do we solve this?
I just guessed and checked answer.
Okay, -1 works, okay. Yes. Okay, so so that's kind of like what we did before, right? So x times x plus 1 is factoring, right? And then this thing equals 0 corresponds to -1, yeah? Or this thing could be 0, which gives you x equals 0, yeah? Okay, so the guessing method actually is helpful when you can't see the factorization, okay? Um, so you'll learn later that if you can guess -1, so if you have a polynomial and -1 works, that is equivalent to saying there's a factor of x plus 1, okay? So if you can see there's a factor of x plus 1, it might be easy to see that x is the other factor, okay? You see, like, yeah. Yeah, so don't ever be like, so it's like, oh, it's like I guess -1, but it's not the way he did it, so it's wrong, right? It's not like that. It still gets there. Okay? It's just you gotta do something else. But at the same time, you should be aware of, I guess, the train of thought we're on as well. You know, because we did do this just before, so that we may be a little bit more biased towards that. But I guess it's good that you made that because I want to make a comment. You can actually do it like that as well. Actually, it was actually a funny story. Like when it's a cubic, okay, when it's a cubic, like there's no guarantee you can factorize it all, right? And we never actually taught how to solve the problem with cubics in class, right? But it was on our test. And there was this other guy, there was one other guy in our class. And I'm like, oh, I know he can't get this one. Because it wasn't taught to, like, it was just, it didn't tick the boxes. He couldn't get it. But then I'm like, I'll just guess -1, or like, I'll guess 1. And then once you guess 1, you can factor out 1 as a quadratic, right? Yeah, it sounds stupid now, but it was literally the only mark he lost in the whole year in Extension 1 maths. He only lost, except for in the HSC, in the school assessment, that was the only mark he lost in the whole year. Okay, it was not being able to guess that -1 was a solution. Okay, and I guess I didn't lose any marks because I did guess -1. Anyway, so okay, back to this. Yeah, but in the end, like we still didn't. Like the school just said, oh, they would round them up to the same marks, and then I lost any chance of Kim. It actually makes a big difference for the state ranking thing. It doesn't matter. So that's a function, okay? Where we're slowly but surely getting there, okay? This is why we need 2 hours. Okay, so we have a limit of a sequence. We also have a limit of a function. Okay, once you know limit of a sequence, the limit of a function is actually very simple. So it actually probably looks easier. So I limit x goes to 3, f of x, and let's say it's equal to 5. Yeah? What is the definition of this sentence? Yeah? Okay. Okay, I'll give you like 30 seconds to see if you can guess a definition. Okay, and then I'll tell you. But you can see the only difference is that instead of an n, it's an x. Yeah? And instead of going to infinity, it's going to 3.
Wait, so is it like if x is like smaller than 3, then f of x equals 5?
Oh, it could be bigger. It could be bigger.
Okay.
If it's smaller, we have like this notation, like 3 minus or something, to say it's only smaller values than 3. But now it can be anything. Yeah. Yeah.
Wait, so is it then just like as long as it's not 3?
Yeah. So listen to what I'm gonna say. You'll spot some kind of theme. Math is very thematic. You understand? Because it's very difficult to come up with ideas. So if you have one, you want to really make the most of it. Okay. And actually, in like the HSC, the questions are like if you understand the theme, you kind of like can guess the answers. Okay. So it's like okay, I can get as close as I want to 5. Yeah. Using the outputs of f, provided the inputs are close enough to 3. Does that make sense?
Close enough.
Close enough to 3. Okay. So for example, I can get as close as I want. So if I want to get like within a billionth of 5, right? I might need like I might need like 3 like to like 7 decimal places, like between 2.999 and 3.001. So if x is between that range, then I'm going to be within that range of 5. Okay. Does that make sense? Let's do a real life example with what we just had. So we had x squared plus x, right? What happens if you sub in x squared plus x? It's like 9, it's 12, yeah? So we have limit as x goes to 3, and it's x squared plus x, yeah? We say that's equal to 12. Okay. So if I want to get, so what if I want to get just within 1 of 12? So I just want to get within 11 to 13, right? Yeah? How close to 3 do I need that to happen? Well, I don't have to get that close to 3, right? If I want to get just between 11 and 13, maybe like something between like, I don't know, we'll try it. 2.5. Maybe that won't work. 2.5 and 3.5. Will that work? Is it obvious that that expression just increasing? Yeah. Actually, when we were graphing it, we got that it was remember it was like -1 and 0, right? So -1 is here, 0 is here. So the graph looks something like that. Okay. Okay, so the point is when you get to 3, okay, the 3 is gonna be like over here. Let's just say it's here. That's gonna be 12, right? And so can you see if you put it really close to 3, it's actually gonna be really close to 12 as well. Okay. So here we have a special case that if the value actually equals 3, like when you sub in 3, it gives you the same value as the limit, which is 12, yeah? And the function is called continuous. Continuous. So continuous is kind of, it doesn't have any breaks. It just keeps, it's connected. The graph is connected. Okay. Alright, so um, yeah, so does that make sense? So it's close enough, but it might not actually equal 3, you know? So I guess that's one kind of way in which people use limits is to avoid actually having x equals 3, if that makes sense. Because sometimes the function is not allowed to input 3. So for example, if it's like 1 over x minus 3 or something, if you put 3 in there, you get 1 over 0. Okay? You're not allowed to put 3 in. Okay? So if you're not allowed to put 3 in, you still might want to see what happens when you put the limit 3. Okay? Yeah, actually, this is another funny example. Okay? Let's look at the function f of x equals x over x. You know? And let's compare this with the function g of x equals 1. What is the difference in x over x and 1? It's a good answer, but it's not the complete answer. It's pretty much no difference, yeah? Because the x's cancel, yeah? Because if your x cancel, you get 1, right? Yes? But what is this? Is that completely true? 100% true.
X can't be 0.
Yeah, so x can't be 0 in that one, but x can be 0 here. Okay? So it doesn't make sense to 0 over 0. You know? It's kind of like implicit in the expression. So there's only one minor difference. Okay? So if you were to graph the functions, one of the graphs would just look like this. Yeah? It's just 1. Yeah? What would the other graph look like? So this is 1. So this is this is y equals g of x. Yeah? It's just literally y equals 1. Yeah? What does f of x look like? This is like more like notation than anything. It looks the same as g, right? Except here. Because there's no value there, right? So what you do when you say except one value, you use an open circle. Have you seen that? Have you seen that in school? So the open circle means it's every point on that line except for that point.
Oh,
Yeah. So sometimes you want to draw like a ray. It's every point on the ray and including this point. Or if you want it to not include the point, you make it like an open circle. It's more notation than anything else. Okay. Yeah, so even though even though there's no actual point there, you can still talk about stuff like the limit as x goes to 0 of x over x. Okay. So implicit in this expression is that x isn't 0, right? So this is actually just equal to 1. Okay. So whereas the g is continuous, the f is not continuous. Okay. Because it has 1 here, but you're not allowed to put 0 into x. Okay. Okay, let's hope this is enough for you to understand the basic calculus thing. But even if it's not, you still got a long way to go anyway. It's like the first lesson. So the first lesson, we show you the beginning and the end. Okay? This is more like the beginning of the end. There's more to the end. Okay, but fundamentally, what is called calculus is this idea that if you have a graph of a function, okay, you can try to calculate the slope of the function at any given point. So if you have like a tangent line, so a tangent line is a line like that just touches the curve, yeah? Okay. And the slope of this tangent line is supposed to be sort of the slope of the function at that point. Does that make sense? Okay. So real life example, if you were like running or driving a car or something, right? And this graph showed like how much distance you were traveling, okay? And then the horizontal axis is how much time you took to travel the distance, yeah? So like so if you're traveling like your speed kind of your distance is like, let's say that's the y-axis is your distance, yeah? And this is like your time, yeah? If I took 2 points on your journey, right? Okay, and I joined the line. I joined the line. Join the line, yeah? From 2 points on your journey. So 2 points on your journey means 2 moments in time, okay? So this could be like minute number 2, and this could be minute number 3, yeah? Okay. And then what's the you guys know slope, right? Just normal slope of a line, yeah? So there's like rise over run. The slope, the difference in the so this is how much distance you traveled in that time, right? Yes. So maybe in the first minute you already traveled 100 meters, and by the third minute you traveled 200 meters. Yeah. So then in that 1 minute interval you traveled 100 meters. Yeah. So can you see that means your average speed is 100 meters per minute? Yeah. That's your average speed, right? So um so that's what that is. But if you had just 1 point, okay, like here, yeah, okay. There's two ways to think about that, I guess. It's one way is it's what's called your instantaneous speed. Okay? So like when you're driving a car, you know how it says what your speed is? Or I don't know if you can drive yet. Almost. Next year maybe.
Yeah, next year.
Next year. But you can definitely see other people driving, and for some reason in Australia you're just always watching the speed. You're not even watching the road because because there's a speed camera somewhere. So you don't even know what's outside of the car. You're just watching the speed, okay? And sometimes, yeah, you run into some cars and stuff. But like it's like it tells you how fast you're going any instant, right? So so that's what the green line really is, okay? And then the question is like, what is the relationship between the green line and the red line? Okay. So instant means like at that moment in time, right? Average means you have two moments in time. Okay. But you see, like, there's not really a difference between an instant and two really close moments in time. Okay. Does that make sense? Or if you can perceive the difference, you can always just take two closer moments in time. Okay. So in some sense, the instant speed is a limit of the average speed. Does that make sense? So you can get as close as you want to the instant speed if you take the two moments in time close enough to each other. Yeah? The language really helps sometimes. Okay, so um yeah, and the first this is called and calculating the instantaneous speed. So if we pretend every function is distance with time, okay? Then if we're calculating the instantaneous speed at any point in the function, that is called taking the derivative. Okay? And doing that is called the differential calculus. Does that make sense? Okay. So it's kind of pretty crazy. It's like, um, yeah. So, I mean, it's not necessarily even possible to do, right? It's kind of like people couldn't even do this before. But then now that people could do it, it's called differential calculus. Okay. And this fundamental idea with limits is, um, well, it's kind of, so basically the idea is it's easier to calculate slopes when you have 2 points. It's impossible to calculate slopes when you have 1 point. Okay. Because you don't know what the rise or run is, yeah? So, but you can approximate the 1 point by 2 points if you have the 2 points close enough, yeah? So kind of like how, um, it's like impossible to deal with round things, okay? But if you look close enough, the round thing basically looks flat, okay? And so the close enough is this limit idea, okay? All right. Okay, we're really running out of time here. This is okay. So there's another thing. There's another thing, okay? So if we had this, um, oh, yeah, I should probably have done speed versus time, but it doesn't matter. So if I have speed versus time, right, it's a bit more abstract now, I guess. So speed versus time is that you're literally plotting what's on your speedo, okay, and you have some curve, okay. By the way, if I took the slope, like if I took the derivative, like the slopes of the speed versus time, do you know what I get? It's called acceleration. I don't know heard of acceleration. Okay, but we're not taking the slopes, okay? We already did that with the differential calculus, okay? Now we're taking areas, okay? So imagine how people figured out the area of a circle. Well, this probably could help, yeah? Let's take areas. Does that make sense? So what is the area? So if we just joined the two lines, yeah? So the area is hard to understand because it's curved, you understand? But if we just joined it, it's straight. It's a trapezium, right? Okay. What does that area represent? Okay. So if the speed was a straight line, right? So if the speed actually was straight like that, yeah, then can you see the area represents the distance traveled? Because if the speed is like, okay, maybe even easier. What if the speed was actually just horizontal? Okay, the speed was constant, yeah, at that point, yeah. Speed is constant, so it's literally just going at like 50 k's per hour, yeah, and then it goes for like 1 hour or 2 hours. You know what I mean? If it goes 50 k's an hour for 1 hour, then the area is 50 times 1, and it's traveled 50 k's. See what I'm saying? So the area of like a rectangle, yeah, is the area, the distance you've traveled. Okay. Um, yeah. So, but what happens if the area is not straight like that? Yeah. Okay. It could be in general, like it could be it could be curved, right? Yeah. Okay. But the thing is, when you look at the points very next to each other, okay, the difference in height is very, very small, right? So in some sense, it's still a rectangle. Yeah. So we can get um, the area by taking enough rectangles of very small width. Yeah. Okay. That's a limit again. Okay. So we can get as close to the area as we want, provided we can take enough rectangles that are small enough. Yeah. So that's very good. We have a way of calculating the area. Yeah. Okay. So this is called integral calculus.
How many types are there?
Just two. Yeah, it's like next 10 weeks I just got like calculus, calculus. I mean, there's other words that end. There's other phrases that end in calculus, but this is the calculus, of Newton and Leibniz or whatever, the stuff you learn in high school. Okay, so you learn how to find the integrals of stuff. Okay. Um. Okay. And this thing that's not really taught, but it's used, and it's one of those weird things that you don't really go into on its own, but you're basically using it without saying it all the time. How are they related? Okay. All right. This is called the fundamental theorem of calculus. Fundamental theorem of calculus. Okay. Um. So let's say it in a few different ways. Okay. So um. Yeah. So if you take like distance versus time, okay, and you find the slope, the instantaneous speed, you get the instantaneous speed, right? Which is actually this graph, okay? Yeah. If you then find the area under the curve of this graph, you get back the distance traveled, okay? So that's essentially the fundamental theorem of calculus. So what it says is if you take the derivative, yeah, and then you take the integral, you get back to the original function. Okay. So the fundamental theorem is really telling you how they're related. They really undo each other, okay? So also, if you take the area, see, if you take the area here, you get back to the distance, right? You take the derivative, you get back to the speed. Okay, so there's the two directions of the fundamental theorem. Differentiate, then integrate, you get back to the original. Integrate, differentiate, you get back to the original. Okay. There's some minor things, like it's not quite the original, it's like the original plus like a constant or something. But we'll get to the minor things later. Okay. So then the entire HSC course, or the entire course on calculus, is really just applying this idea to all the functions that you've probably already all been introduced to by now, okay? So the polynomial stuff, yeah. So you learn how to differentiate them, you learn how to integrate them, okay? The next thing you don't learn is the I think it's called the trig stuff, yes? You learn trig functions, cosine, sine. Yeah, so then you learn how to differentiate them, integrate them, and various applications, okay? There's also other reasons to differentiate them, integrate them. Like you can find the maximum and stuff. Because see, like the maximum occurs like when the slope is 0, right? That's a way to find the maximum. So that's like saying that is like 10 marks and like there's 10% of your HSC. Okay. And then what comes after cosine and sine and trig functions, do you know? Okay, it's the so-called exponential functions. Have you heard of those? Logarithmic functions. Yeah, so log and exponential are inverses of each other. Okay. So basically all the things on your calculator. Yeah. Yeah, so if you look at the book, okay, we've still got a bit of time. So if you're looking at the book, like here, if you look at the contents, did you bring your book? Oh, okay, it's alright. Maybe bring it next time. But like, if you look at the contents, it's pretty much following that structure. Yeah. So it's the functions, polynomial, trig, and what you call it, exponential and logarithmic. And if you do that thoroughly, you probably cover all of extension 1 and maybe a little bit of extension 2. So extension 2 has like topics like proofs, which is kind of like a weird topic because they don't prove anything or define anything. It's kind of like, it's almost like you'd think that you wouldn't teach proofs so that no one would expose the lack of proofs and everything. Okay, but there's a subject called proofs. There used to be 8 topics, and the test used to have 8 questions, and it was like 1 on each question. But now it's like they condense the topics into each other. So then they have another topic called polynomials and complex numbers. So they put that together. Okay. And they used to have a topic called curve sketching, but maybe it combined with something else. Okay. And then there's like this weird topic called mechanics. Okay, which is literally just applying this stuff to physics. But like, I think if you understand it well, it should be really easy to apply to physics. Yeah, and then there's kind of some miscellaneous topics like 3D vectors and stuff like this. Okay. So if you just learn the calculus, you don't cover all the topics up to 4 unit. I think you cover all of it up to extension 1 plus like a third to like a half of the 4 unit topics. Okay. But if you do it well, I think you'll prepare your mind to be good at the other topics too. Does that make sense? Because like, what is proofs really? It's really just like, I'm trying to tell you a proof of something, okay? And you understanding that to be true or false, right? And if you can understand that properly, so understanding properly is not just understanding all the things I'm saying, because if I say something wrong, you have to also pick that up. It's just that I guess I don't necessarily say the many things that are wrong because I've said them the same thing so many times. But like, you know, so at school you can practice picking up on people saying, because sometimes you can say the wrong thing many times and never catch it. So you can try to pick up on people saying wrong things and try to ask, oh, why is that true? I don't know. Like if you watch just like YouTube or some like people's proof of Pythagoras, they're all kind of not correct. Okay. Um. Yeah. Okay. Do you guys have any questions about this? Okay. Try to think of a question even if you don't have one sometimes, because it makes you think about stuff that you might have taken for granted. Um. I should give you an example, otherwise we kind of the algebra needs to be used. Okay. Okay. So if we do a derivative, so this is called derivatives from first principles. Okay. Take something very simple. So you have like y equals x squared. Okay. How do we find the derivative? Okay. So the derivative sometimes you write as dy dx, or if you have f of x equals x squared, the notation you might use f prime of x equals whatever it is. Yeah. Okay. So you usually, when you first learn it, you learn how to figure out first principles. Yeah. And there used to be, and I think there sometimes still is, just like a question that's like, prove the derivative is this using first principles. It literally tells you how to do it. Okay. But then aside from that, you're kind of just using like blocks of calculations that you already know how to do to compute derivatives. Like you're literally given like a sheet, like a table of derivatives in the exam, like a formula sheet.
Oh yeah, I think I've seen it.
It tells you what the derivative of like all the basic things are. Okay. Um. Okay. So what is this from first principles? So basically, what you're trying to do, you're trying to find the slope of a tangent, right? You're trying to find the slope of this tangent. Okay. But we don't know how to do that. That's the problem. Okay. So the slope of this tangent is, you know, f prime of x, where this is x. Yeah. Okay. So what we don't know how to do that, but what we do know how to do is we know how to find the slope of a secant. Okay. The secant just means it touches twice. The slope here is x plus h, right? So can you see what? So this is f of. Can you see what this is? So I'm taking a secant that's h away from x, yeah? So the input's x, yeah? What's the y value? So the x value is x and the x value is x plus h. What's the y value? Hmm. So we don't call it. So we call it. See the y value. So we call it if it's x, it would call it f of x. Yeah, that's the output. Yeah. Here f of x plus h is the output of x plus h. Okay. Okay. In this very special case, yeah, it's actually x squared, right? And x plus h whole squared. Yes, because this particular function squares things. Okay. Okay. So this, what's the slope of the red line? What's the slope of, you know?
Is there just the difference between the two y values and the two x?
Yeah. So in general, it's f of x plus h minus f of x over h, right? But specifically in this case, it's x plus h squared minus x squared on h. Yeah? Okay. And so the idea is if I can get like if I can get as close as I want to the black line using the red line, provided h is small enough, yeah, or h is close enough to 0, yeah. So then I say this is a limit as h goes to 0, okay. So this is the definition of the derivative, okay, yeah. And in this particular case, it's equal. So in this particular case, it's equal to the limit as h goes to 0, x plus h squared minus x squared on h. Okay. Okay, so I want to be able to calculate this. Okay. How do we calculate this?
Like expand and simplify.
Yeah. How?
Like, cause like x plus h whole squared is x squared plus 2xh plus h squared, and then the x squared is cancelled. And also the h is also cancelled.
Alright,
So
you see what he's
2x plus h.
okay. So you cancel this with this, alright, and you get that left. Yeah. Can you see there's actually another way to do it? I mean, the factorize is one thing that helps. I mean, they both end up there. It's just I want you to be aware you can factorize the difference of two squares. Yeah. You know the difference of two squares?
Oh yeah,
What do you get?
you get x plus h plus x, x plus h minus x.
Yeah. So what's that? That's x plus h minus x is just h, right? X plus x plus x. So you get the same thing, but you have the h factor. Okay. So your method still works. I just want you to know that. Remember how we are saying if there's fractions, you kind of look for factorizations. There's kind of these little things. No one will ever tell you these things. I know for a fact because all of my high school, no one ever told me any of those things. No one. Okay. And yet they're true and ubiquitous. Okay. So so that makes you kind of wonder, right? It's like the kind of like if you see a factorization and it saves you time, that time over the course of your like 2 years of HSC probably add up to like hundreds of hours. Okay, so this is hundreds of hours worth of time saved. And if you save like an hour on your 3 hour exam, then like you know that's a pretty big deal. So all right, okay, and then what did you do next? Slava already did this, but what do you guys do next? Okay, so remember like what I was saying about factorizing. So one of the reasons you factorize when there are fractions is so you can
Cancel
cancel stuff
h.
out, right? So here the the factorization helps you cancel stuff, and so that's something natural to see. Yeah. Also, we really need to cancel the h because we can't have h is equal to 0 in the denominator. Okay, and this is the whole point of the limit. Yeah, is to avoid the 0. Yeah. So now what do we have? Limit h goes to 0 of 2x plus h. Yeah. Okay, so there's lots of ways to finish this. Um, so there's like this thing, like we have limit laws where it's like if the limit of a sum is the sum of the limits, so you can just add them separately. Okay, but maybe I can convince you because of what I've said already today. If I was just to say this was 2x, would it be that much of a stretch? Okay, so what would it mean for it to be 2x? Okay, I can get as close as I want to 2x, provided h is close enough to 0. You know? And it's literally 2x plus h, right? So what does close enough mean? Well, what's the distance between that and 2x? The distance is literally h, right? It's 2x plus h and 2x. The difference is h, right? So I can get that difference as small as I want, provided h is small enough. Yeah. So whatever I just need to make the h whatever the difference is, because then it'll match, right? So if I want it to be within a billionth of 2x, I just make h a billionth, because h is exactly what the difference is. Yeah. So you can see that limit by definition is 2x. Okay. So what we proved was that if f of x equals x squared, then f prime of x equals 2x. From first principles. Okay. Yeah. So in theory, right now, in principle, you have what it takes to be able to prove actually a lot of different derivatives. Yeah. You can just apply this method to lots and see if you can get to the end, right? There'll be other methods that'll help you get them faster, right? But right now, I think this is kind of nice. Like when you encounter a function, you're like, oh, can I figure out what its derivative is? Okay. I mean, not all functions are differentiable, but basically all the functions you have in class are going to be. Okay. So one thing is like, so continuous means it kind of like it connects. Yeah. Intuitively, differentiable is a bit stronger. So it's not just connects, but there's none of these kind of sharp points. It's more like smooth. Okay. And real life, in some sense, is differentiable. Okay. Because like even like even if you're like running, right? You can't really suddenly stop. You know what I'm saying? Like it always takes a bit of time to stop.
What if you
So
hit
like
a
you're never
wall?
like yeah, like unless you hit a wall, but that's super unnatural, right? But like so if you're running, right? Like you're gonna kind of stop or slow down and then stop, right? Yeah. So if you hit a wall, then yeah, but that's probably the end of the function anyway. So it's not gonna keep going to be smooth. It's just ended. Okay. Oh, that's it, guys. That's a lot to take in, isn't it? Um, yeah, yeah. I think there's some things if you invest in at the start, you'll get quite a lot out of it later, right? Okay. Do you have any questions? You guys seem to follow pretty well. Yeah. Okay. So
But
what's the
is it that we're
derivative of
good
x
at?
squared? Huh?
I was gonna say, is it that we're good at following, or is it we're good at pretending to follow?
No. Well, I asked some questions. I got some answers. There's some things that
Yeah.
like there's some things like I could have given you any reason you would have accepted. I understand that from experience. Okay. But I did give you the right reasons. Okay.
Yeah.
Like um. And there's some things I think like giving you the right reasons. It's more just like a habit. It would make little difference if you if you had the wrong reason. But I think in the long term though, like it would make little difference for this proof, but I think it would make a difference for other things. Because if you use the right reasons to accept things, then you'll accept other things because they're right. But if you use the wrong reasons, then you start accepting wrong things for those reasons too, right? Okay, and this is what made calculus such a like a people learn calculus to see if they're smart enough to learn calculus. It's not really like they learn calculus to build bridges, you know. But obviously, people do learn calculus to build bridges. Um, so there was a time where calculus wasn't considered maths because they couldn't prove everything. Yeah, like they always had these ideas. Yeah, these ideas came a lot earlier than it was called calculus, like the maths topic. Okay, but it was considered like an intellectual achievement for people to be able to actually put these ideas down with certainty, right? In such a way, like that it became kind of almost easy to do. Okay. No. Yeah, so even if you're just doing advanced, like you'll still be doing this. Okay. You'll still need to do the derivative of x squared e to the x cosine x. It's just that when you do extension 1, you'll probably be doing, I guess, more difficult integrals and stuff. Yeah. Okay, I'll try to start a Discord channel for us. Okay. And then, yeah, if you're interested, maybe you can tell me what the derivative of x to the n is for homework. Okay. What is the derivative?
Wait, can I
Okay.
guess right now?
No. And if you don't really have an idea how to do it for x to the n, you can just do it like n equals 0, 1, 2, 3, or whatever you're comfortable with. Okay. And also, this whiteboard is on it's infinite and permanent. It's on the Discord server as well. Okay.
Wait, how infinite is it?
Well, we never really tested it.
Like, would it start bugging out if I scroll far enough out?
It does lag. I mean, so it takes a while to load when it gets a bit full. Yeah. So it's just approximately large. Is it just large? Yeah.